Welcome to our battery charging strategies webinar. Today we are going to talk about battery charging strategies, but more importantly, get into topics that may not be well known for everyone. Unless you're really into the battery applications, this might be topics that are not often discussed. With us today, we have Bjorn Vasiden. Bjorn has been with PowerSonic now for over 4 years, and he is heavily involved in just about any battery application since he is in the applications engineering field for PowerSonic. And also joining us is Tom Denny. Tom has had 4 years of experience here at TRC Electronics, but his battery knowledge goes far beyond his time here at TRC. We usually go to Tom whenever we have a battery question. He's our go-to local guy for batteries. So before we get started into our discussion, let's just give an overview of what we're going to be talking about today, so everyone is clear. So the first thing is SLA versus LiFePO batteries. This is our primary focus. Will be on the SLA side, because that's where they're going to be most affected by long-term storage. We're going to have a section about that. We also have charging strategies. What does multi-stage charging mean? But also get into application-specific voltages, which are also very important. Battery storage is a nice topic as well, because that's where we have to be careful in how batteries are stored, but also not just in effects of temperature, also how much time those batteries are going to be in stock before they need to be recharged. And then selecting a charger, that could be a topic all on its own, but we're going to go over the overviews of what are the best practices for selecting a charger. And then finally, share with you what is TRC doing in order to keep their batteries fresh and always available, always topped off, so that if they're in storage for long periods of time, we still have those batteries able to be sold at a higher level of charge. All right, so I guess we'll start with let's get right into the SLA versus LiFePO. And Tom, why don't you walk us through this one?
Sure. So I have a table here just comparing a lead acid battery versus a lithium iron phosphate battery. And these two batteries are somewhat similar in the sense that they're both about 12 volts and they're both 100 amp hour. A couple differences to note here. The lead acid is 6 cells at a nominal 2 volts, while the lithium iron phosphate is 4 cells at a nominal 3.2 volts. They can both do two-stage, three-stage, or four-stage charging, depending on the type of charging being used. Initial charge current is a little bit different between the two. You want a little bit of a lower initial charge current for lead acid. Here we have 0.1 C versus for lithium iron phosphate, we generally say 0.25 C. And then charge voltage, even though they are different volts per cell, it multiplies out to be that they're about the same voltage per battery. So 13.5 to 14.7 volts approximately per battery. Finally, a little bit of difference between the storage, lead acid at 100%, lithium iron ideally at 50%, and a higher self-discharge rate for lead acid. Going back to the charge current there, charge current that we have here is 0.1 C for lead acid. Bjorn, could you just explain what is C exactly here?
Yeah, so C is sometimes mistaken, but it's really just simply the capacity of the battery. So anywhere we see whether it's a zero point 0.1 C or a C over 10 or 0.25 C or C over 4, we're simply referring to the rated capacity of the battery. So in this case, it's 100 amp hours. So zero point 0.1 C or C over 10 is 10 amps. And 0.25 C, or in some cases C over 4, is 25 amps. And you'll see that written differently by different people, but anytime C is being called out is simply referring to the capacity of the battery. And the reason it's different between lithium and lead acid is simply because there's a different chemical reaction occurring. So we want to keep heat down in both cases, whether it's lithium or lead acid. Heat is always the enemy. And in order to keep that charging temperature low, we have to keep our standard charge current for lead acid lower than our standard charge current for lithium. So you're always trying to balance life of the battery with the speed at which you're able to recharge the battery to then again deploy it.
So that's interesting because when we got into the battery charging process here, we came to realize the amount of energy that you could actually put into a battery. And Tom, maybe you can just share with us, like, how long does it take for us to charge a SLA battery when we're actually pulling them in stock to refresh them?
Sure. So right now we're charging at float or kind of a high float. So we're putting a good 16 hours into the battery to make sure it gets up to a full 100%. Now, if we did a higher voltage, we could charge it a little faster. Kind of just depends on that.
But
I wanted to ask you, a lot of times we see there's a little bit of a higher charge rate listed on data sheets. Like, you'll see 1C sometimes listed for lithium iron phosphate. Why do you generally recommend this lower?
Yeah, so that's a great question because you absolutely can charge the battery faster. So PowerSonic for lead acid, we recommend a maximum charge current of 0.3 C or C over 3 for lead acid. And for lithium, it's C over 2 or zero point 0.5 C. And that being, the idea there is some places you may want to trade the life of the battery for being able to recharge the battery quickly. So it's more important to charge the battery quicker for an application where you can't have that downtime. And it's okay if you take a little life off the end of the battery. That's certainly acceptable. But what we want to recommend is the best case scenario to get the maximum life out of the battery.
Yeah, and especially if a client is buying a battery out of stock and they are assuming that the battery is brand new, we have to keep that charge current at the stated levels so that when that client gets it, he knows he's getting a good battery that's with the longest life.
Absolutely.
That's awesome. Let's move on because we need to talk about also the different charging stations, charging stages that you have, and some of these charts can get complicated. So let's just walk through some of these and define what do these stages really mean.
Sure. So I can start off there. So generally, you only have three types of stages when it comes to battery charging. You've either got constant current, constant voltage, or rest. But then there's different kind of nuances within there. Stage one is basically almost always going to be constant current. You're pumping as much energy into that battery as fast as possible. And then you go generally into a constant voltage stage, but that can be either boost charging or float charging, depending on the way your stages are set up. Boost charging always being at a little bit of higher voltage. And then if you have three-stage charging, you're then going to go into either your float stage if you're doing just three-stage charging, or a rest period if you have four-stage charging. And then if you have four-stage charging, stage four is basically always going to be boost.
Yeah, and I think an important note here is there's really three true stages of charging that we go over here, but you may see marketing of 5-stage charging, 8-stage charging, 10-stage charging from various charger companies. And it's important to note that they're using these three stages, but they're also adding evaluation stages. So their first stage might be under relaxing, what is the voltage of the battery? And then it might apply a very small charge for stage two, and it's watching how the battery is reacting to evaluate the health of the battery before it moves into these two true 3 stages of charging. So when you see a charger that markets like 8-stage charging, it could be 3 stages of evaluation, 3 stages of charging, rest, and then boost, and then more evaluation. So it's just important to note that even though some people may say they're doing more than 3 stages of charging, when they're actually charging the battery, it's always these 3 stages.
Right. And before we move on, we have a couple of questions here, and they're actually timed that I don't want to just move on without actually staying on the subject. One of them is from Josh Case. He asks, is it true that you can constantly fast charge batteries? Will it reduce the overall life? And is this the same for either battery chemistry? So Bjorn, maybe you want to take that question and just highlight those.
Yeah, so fast charging is always going to come down to heat. So if you have a method of cooling the battery, you can charge it faster more times. So if we use an example like an electric vehicle where the battery's temperature is being actively monitored and maintained by a cooling and heating system, they can quickly charge the battery many, many times because they're controlling the heat. Often with industrial batteries like our lead acid batteries for standby and cyclic applications, whether it's an alarm panel or a motor scooter, the battery's heat is not being actively maintained. So if we use the motor scooter or mobility scooter example, if the OEM of that motor scooter was to do fast charging over and over and over again without controlling the heat of the battery, it's going to reduce the life because you're when you heat up the battery, you're basically drying the battery out and not allowing that chemical reaction going on in the battery to occur.
That's right. And the other follow-up question he had was, do we store batteries at full charge? So Bjorn, I know that when we receive batteries from the factory, we actually have a charge date on them. But can you just elaborate a little bit more on that one?
Yeah, so the state of charge of the battery is going to depend on the chemistry. A lead acid battery, you want to keep fully charged as much as possible, and that's just due to the nature of how the battery decays and breaks down. We'll get into that a little more, I think, as we move on in the presentation. And then for a lithium battery, you actually want to store it as close to 50% state of charge as possible, and that's to balance the charge across the cathode and anode on the battery.
Right. Awesome. Let's move on to, I know that David has a question, but I believe we'll be able to answer this question right after this topic. Let's talk about standby applications versus cycle applications. And quite frankly, this is something that for us, it's been a big takeaway because when we're now with customers, why do we ask them what the application is? This is going to actually let us know the reason why we need to know specifically how they're using that battery. So, Tom, let's talk about what standby versus cycle means, and then we'll also give a couple of examples on the applications themselves.
Sure. So your standby application is kind of going to be your UPS type application where you've got the battery always there, ready to go. A lot of people keep those at float. So that's why you see here 2.25 volts per cell is a pretty standard float voltage that will keep the battery at 100% all the time. Cycle application is where you're going to be constantly discharging the battery, recharging it, like the motor scooter that Bjorn was just talking about. You know, it's going to be possibly discharge it and charge multiple times a day, I guess, depending on the size of how often you're using it. And then you get a big difference here as far as cycle life goes between lead acid and lithium. Bjorn, do you want to talk about that a little bit?
Yeah, so the just kind of the nature of the lead acid battery, it lends itself to the standby application because it is really good cost for performance during standby. So the battery, when it's not being called on to discharge regularly, you're not actually degrading the battery that quickly. Whereas you can see in the bottom right where we compare the cycle life of lithium to lead acid, lithium in standby, you're really not taking advantage of the battery's capabilities. Whereas in cyclic with lithium, you can cycle that battery so many more times. That's when lithium really starts to pay for itself.
Yeah, and that's an important point because you can have an SLA in an application where you're cycling it on and off. And actually, we do have a customer right now that's looking for a type of battery where they need to go for 6 hours before recharging. So if we specify an SLA because all they care about is cost, what's going to happen after, 300 or 400 days? We're going to end up with having them replace the battery, and then they're wondering, well, this battery was supposed to last 4 years, and it didn't even give me more than a year.
Yeah, it's supposed to last 3 to 5 years, sitting on a shelf, not 3 to
Exactly.
5 years cycling.
Right. And before we move on, guys, there is a question from Dave, and Dave asks, are SLA statistics the same for, say, an automotive type battery, or are they designed to operate in rough conditions? So Bjorn, I think you may want to take this one and just explain like what some of the differences are.
Yeah, I think we probably don't want to get too far into the weeds on SLA battery construction, because we could probably have an entire shop talk about that on its own.
Mhm.
But there are differences in construction of starter batteries versus standby batteries versus cyclic batteries versus high rate batteries. At the end of the day, what you need to know is if you're going for deep cycles, you want thicker plates. If you're going for high current, high rate, you want more thinner plates, and we make all of those changes in our battery line. So an engine starting battery is very high current and high vibration. So an AGM thin plate battery is going to perform the best there, and that's because you're holding the plate still, and you have those thin plates for high current discharge. In something like a flooded engine starting battery, that's a commodity product, right? So you can still have thin plates, but without that AGM separator in there, the plates are going to vibrate around, and you may get internal shorts sooner, which is going to end the life of the battery.
That's great. I have another question about quantitative data, but I'm going to save that until our Q&A, just so that we can get that that participant on our Q&A session towards the end.
Okay.
So that's great. Let's talk about selecting a charger, because quite frankly, this could be another talk on its own. We've had many questions that came in since we started bringing batteries onto our line on the different types of chargers that we offer. And it's really not as trivial as everybody seems to think. Not only that, just by reading the data sheet, that doesn't give you enough, and really need to dive a little bit deeper. So Tom, walk us through some of the charger selections that we've experienced here.
For sure. Well, so one of the first things you want to look at, of course, is your voltage. Whether you're dealing with a 12-volt system, a 24-volt system, or a 48-volt system, that's going to be number one, I would say, in selecting your charger. Also, your application, as far as whether it's cycle versus float, and whether or not you can hit those voltages that you need for the cycle charge and the boost charge for there. Number two, I'd say, would be power, also incredibly important. So that's going to really affect your initial charge current, because your voltage times your initial charge current is going to give you your power. And then you're going to want to look into whether or not that's adjustable for certain applications, because you might be able to pick a slightly higher power supply, but then lower your initial charge current. Number of stages, we talked about a bunch. That's going to be important, whether or not you have 2-stage or 3-stage, or which one you need. And then whether or not the charger is programmable and what kind of features it has. On the left here, you can see I've got 3 different types of chargers kind of up at the top there. There's a wall wart charger, kind of a smaller charger. At the bottom, NPB450, that is a very programmable charger. It has CAN bus. You can do all sorts of things with that. Also pretty high power. And then in the middle there is actually a really big guy. It's bigger than it looks in that picture. It's an NTN5K. It's a 5,000 watt power supply. Sorry, 5,000 watt inverter that will also charge batteries. So it's an inverter charger combination.
That's great. Now, one of the takeaways that I actually had when we were looking at chargers is when we look at a manual and it says, okay, this charger is good for 35 amp hours to 150 amp hours. I mean, that's just one single piece of data. But if we go back to the C ratings that we just talked about before, it may not necessarily be the same. So, for example, if you're having a charger that is got a minimum amp of 10 hours, I'm sorry, 10 amps, but you only need 1 amp for the battery to charge per its C rating, you could actually then bring that battery, you could actually boil the plates with that battery. Is that true?
Yeah, that's absolutely true. So, it's not a perfect world when you're actually out in the application, and you may not always be able to hit 0.1 C or 0.25 C with how the charger is designed for the application. So, what do you do in that situation? And if it's an example like that where the C over 10 is 1 amp and your charger, its lowest current is 10 amps, you're absolutely going to damage that battery by charging it too fast. But what if it's a 2 amp charger, right? Well, now you're kind of looking at I'm going to charge the battery a little faster, and I'm not going to charge it above 0.3 C. So it might be worth it to me to accept that slightly faster charge, knowing I might reduce the life of the battery a little bit, but it's going to be okay. So whenever you're sizing that, if say that there's also a half amp charger, so you're desiring to charge the battery at 1 amp and you have a half amp available and a 2 amp available, which one do you choose? Well, you have to ask your customer, do you want to charge a little slower and extend the life of the battery? Or do you want to charge a little faster and accept that reduction in life, but your recovery is going to be much better? So it's kind of that line you got to walk of, you may never have the perfect charger, but there's a benefit to going each way.
Right. And then now let's throw in there series and parallel combinations. And Anthony has asked us a question. I'll just read it. So if he has two banks of 4 batteries wired in series parallel, each battery is 12 volts, 55 amps. For me, this says I need a charger that can charge a 48 volt of 110 amps. Is this true? And if it's not true, what should it be? So I guess we got to just take out a little piece of paper here. So he's got 2 banks of batteries, of 4 batteries. So he's
Yep.
got 48 volts.
Yep. So the total capacity of the string is 48 volts at 110 amp hours. That is true. So you're wiring the batteries in series, and then you're wiring that string of series batteries in parallel. Is that correct?
Yeah, so eight batteries total, I think is what he's saying there, right?
Yeah.
Okay.
Yep.
And you chatted yes.
Yep. So that's exactly right. It's a 48 volt, 110 amp hour string. And what you'll want to work with is those charging voltages that were listed earlier in the presentation. So for cyclic charging, you'll want to do 2.45 volts per cell. So if you look at 4 batteries in series, and each of those batteries has 6 cells, somebody will have to do some quick math, but it should be 24 cells. And
yeah, I think
so
you're
24
57 point.
yeah, 24 times 2.45 might be easier to do 14.7 times. Yeah, it's going to be around 55 volts.
Right. So now, actually, this is interesting. When you put batteries in series, they're not all going to be the same voltage because they could be at different stages. So maybe just take a minute to just explain that, because this is going to be really helpful for those that are charging batteries in banks without realizing this.
Yeah, so it's absolutely critical when you're charging batteries in strings to charge them individually before connecting them in series. So if we take an example of a string of 4 batteries, and 3 of them are at 100% state of charge and 1 of them is at 80% state of charge, if you start to discharge them, that battery that's 20% low is going to hit 0% state of charge when all the other 3 batteries in the string are still at 20%. What's going to happen if you continue to discharge is you're going to cause irreversible damage to that low battery until you get to your termination voltage. And then let's use the reverse. Let's say that now you're recharging that string and you have 1 battery that's at 0% state of charge and 3 batteries that are at 20% state of charge. When those 3 batteries get to 100% state of charge, the charger isn't going to know to turn off because the overall voltage of the string is still low. So it's going to continue to charge. And now you're causing irreversible damage to those 3 batteries that are already at 100% state of charge. So it's very, very important to ensure that all the batteries are fully charged, then connect them in series, and then deploy them in your application. We also recommend every 3 to 6 months, removing the batteries from series and parallel, rebalancing them, bringing them all individually to fully charge, and then redeploying them in the string.
That's great. Let's actually, and that brings up a good point. Let's move on to storing batteries, because this is a topic that, unless you're actually storing batteries and have experience in that, there are things you may not be aware of. So Tom, just walk us through the capacity retention versus temperature and also, what happens over the life of that battery.
Sure. So yeah, what this graph is really showing is the high impact the temperature can have when you're storing SLA batteries. On the left there, you can see capacity retention ratio. So that's basically how charged the battery is, state of charge. On the bottom, you're seeing time in months. And then each line shows a different temperature there. So if we say go with the 20°C temperature there, which is a little chilly, that's colder than I keep my apartment. That by 6 months in, that battery is down to 80% charge. And once that battery starts getting below that, you can start causing some damage to the battery, right, Bjorn?
Correct.
Yeah, so definitely want to keep those batteries charged if you're going to be storing them for a period of time. You can't just like leave them on a shelf for an extended period.
That's great. I know that Dave has some questions. Dave, we're definitely going to get to some of those towards the end. So just stick around because I think it's going to be very valuable that we talk about some of those points that he brings up. Let's go into the next slide. Talk about what happens with plate sulfation, which is when we're improperly charging batteries.
Right. So yeah, if we leave those batteries discharged, or if we leave them on a shelf for an extended period of time, the acid starts to separate. You start to get more water touching the lead, which is going to create sulfation, and that can permanently reduce the capacity of the batteries. Bjorn, can you talk a little more about what happens there with sulfation?
Yeah, so essentially sulfation is a chemical reaction occurring inside the battery where we're essentially allowing, not really allowing, but what's occurring is the lead plate is no longer able to create that voltage potential in the acid because of the sulfation itself. So it's compounds in the acid that are attaching themselves to the lead plate, and what essentially happens is the battery is no longer able to move charge from the positive to negative plates, and you lose your voltage potential, and the battery becomes unusable.
Yeah, that sulfation can be very hard to remove. Also, I know that sulfation can end up kind of breaking through separators, right?
Yeah, correct. In really extreme cases or in high vibration environments, like what we were talking about earlier with automotive batteries, that those sulfation crystals can actually start to work their way through the AGM separator and cause micro internal shorts. And when you have any sort of an internal short between the cathode and anode, there is no voltage potential. And when there's no voltage potential, you don't have a battery.
Yeah, you'll be below 12 volts and your battery's just basically, it's anything you put it in is going to consider it dead.
Yep. Now it's a lead door stop. It's not a battery.
Right.
Right, exactly. And let's move on to temperature and standby because here, this is where it's important in the application that we really understand where this battery is going into, especially when we're using it in standby applications like a UPS system. So let's just briefly talk about this and what happens to the float life versus temperature.
Sure, yeah, Bjorn. So this is a graph of float life and use. It starts with a 5 years. So this is based on a 5-year battery, right?
Correct. Yeah. So the theme with batteries, whether they're lithium or lead acid, is heat is really the enemy. So anytime the temperature is high, you're just accelerating that degradation that's occurring in the battery. This, like you mentioned, is a standby graph for one of our general purpose lead acid batteries. If you look at our more long life, like our PG line, it's a very similar shape graph. It's just instead of 1, 2, 3, 4, 5 up the years, it's 2, 4, 6, 8, 10. And the real difference is we're adding more lead to the battery to allow it to last longer.
Is the higher temperature basically accelerating the chemical reaction? Is that what's happening there?
Correct. Yeah.
And so that's starting to breaking down the lead faster, right?
Yep, that's exactly right. It's corrosion and sulfation.
Right. Okay. Yeah.
Great. We have one last topic that we wanted to bring up, and that is what we are doing here at TRC in terms of charging batteries. So we're a stocking distributor of PowerSonic, and we're purchasing batteries, storing them ready for shipment to our clients, and we come to realize that if we're holding on to that battery for a longer period of time, they need to be boosted. So, Tom, why don't you walk us through some of what we're doing here to ensure that when batteries ship, they're shipping fully boosted?
Sure, yeah, we want to make sure that our batteries do not fall below 80% capacity. So what you can see here on the left is a battery charging station we created. We actually have 4 separate charging stations here. We're currently charging 4 sets of batteries, and we can do a number at a time. In the other picture there, you can kind of see we've got, I think, 70 batteries, I think that was, in a series parallel combination. So we've got them all in series sets of 5. Charging at 13.8 volts per battery or 2.3 volts per cell. And yeah, we charge these for 16 hours then in this location. We kind of base this off of a charging setup that PowerSonic is using as well for their charging stations.
And from what we've seen, also we may get from time to time. It's like, well, can I have a battery that's fully charged and actually charged right to capacity right from the start from shipment? And we are able to offer that type of a service where we can boost batteries prior to shipment. We just realize that's a service that may also extend the shipping time by at least 2 days because if you're going to want that service, we're going to charge that battery for a full 16 hours. Bjorn, just highlight who needs this type of a service.
Yeah, so it's often critical applications. So places like the medical field, for example, where the battery needs to be deployed at 100% state of charge because there is no time or option for the battery to be charged before it's used. So if the battery was to arrive after sitting on a shelf for say 4 or 5 of the 6 months between boostings, the battery could be at 80% state of charge and 80% state of charge may not meet the requirement when it's deployed in that application right away. So if the battery didn't have time to recover, for some reason, say that if it was a medical cart, for example, and the technician replaced the battery and then didn't plug the cart in, now that cart goes to be used at a not fully charged state. So it's lots of applications like that where battery arriving at 100% state of charge may be non-negotiable.
That's great. Well, thank you all for that. We are going to open this up to questions. Before we do, Dave Hannum, who I happen to know, we've been talking together for a couple of months now, and he has a question here. So, well, he makes a statement that what we talked about the series parallel not being practical in the field, and we can't go out and disconnect batteries from series or parallel charge and then reconnect them. So let's unmute Dave. I'd like to hear more about this. And now that we have Tom and we have Bjorn here, just I'd like to get a little bit more of an understanding of that because we might have a solution for you. Dave Hannum,
Yeah, I was just waiting to be unmuted.
there you go.
Okay, well, we've got 40 towers out there, plus or minus, and we run most of our systems on 48 volts. So we were running four. They're called interstate group. What we've been using is interstate group 31. They're truck batteries. Is what we found was practical, and then price wise, because they're new batteries, but they're blems, so we get a deal on them. So anyway, that said, I do know we don't get a tremendous amount of life out of them because of now this seminar is explaining some of that, but I'm not sure there's a good trade-off for us. You're talking about each battery needing to be charged individually. That's not going to happen in our situation. I mean, when you got 40 towers, you might have power outages. We're in a very rural, hilly area. It's hard to access many times. Power outages when you got the snowstorms or windstorms, whatever. And our batteries are in standby. Fail over for when the power goes out. But then they're automatically. We want those things to start recharging right away. And a lot of times this is evenings, overnight, weekends. I mean, just the idea of going out and keeping them disconnected and then charging them individually, that ain't going to happen. So, I mean, there's, I'm not saying, I'm
Yeah,
not disputing that what you're saying is the best case scenario, but it's not a real world scenario, and
Yeah.
at least in our situation.
yeah, and that's absolutely true. I mean, we understand that in a lot of applications that it's not possible, but we want to outline the best practices so that there's a way to go out into the field and understand how you can make this system perform better. So while it may not be possible to balance the batteries in the field every 3 to 6 months, at a minimum, they need to be balanced before they're installed, right? And it's always a trade-off. So you don't need to go out in the field and rebalance them if you can accept a slightly shorter life. And then the other possible way to prevent this is to use a battery balancing system. So there's actually active systems on the market where your string of 4 batteries that's acting like one 48-volt battery can be individually monitored and charged with an external system actively while deployed in the string. So it's basically, rather than your load or your application seeing a single 48-volt battery, you have this monitor that's actually keeping track of each battery individually. But again, it comes down to a cost benefit. Are you gaining enough life out of the battery installing that expensive system? Sometimes the answer may be no.
Great. So, and Dave, I think in your application, from what I've seen, it's obvious that you have to have a battery replacement schedule if you have multiple outages. But if the cycles are a few times a year, it's just a matter of, I think that would actually give you enough life of the battery to be able to have a more economical application. I don't know if you can comment on that.
Yeah, I'm going to tell you, yeah, we have a maintenance, we have a schedule on the batteries. We actually replace them after they get probably about 4 years of age on them. There's some batteries hardly ever get cycled. I mean, they hardly ever come out of float because the power's reliable there. We've got other sites that I've got one site where I think last year there was a 2 month period where the power went out about 15 times each month.
Oh,
There
wow.
for a while. The power company's having a lot of problems in that area. So anyway, yeah, I it's probably in our situation, it's probably better that we just, you know, we kind of thought we burned the batteries. I mean, we just go ahead and use them. Price wise, I just think we don't run a high enough markup on our product to with a internet service that we can afford to put a tremendous amount of money into, like you talk about, a balancing system or something like that. That's just not going to be practical for us. So probably just what we're doing uh, and is probably the way we'll continue to go, at least for now. But this has been great education wise. I've learned a lot about how batteries work and the life cycle of them. That's for sure.
Well, thank you,
Excellent.
Dave.
Glad to hear that.
I appreciate that. We have a couple more questions that I want to get to, and one is Anthony, and I want to stick on this topic, and then I'm going to get to Gang. What would battery isolators solve issues with higher charge batteries discharging into lower charge batteries if I had, let's say, two banks of 4 batteries I talked about earlier? Why don't we just let's unmute them and let's get a little bit more context there and see if we can answer your question.
Yeah, Bjorn, is this basically the battery balancing thing that you were talking about earlier, the battery isolators?
Yeah, more or less. If he wants to step in, feel free to interrupt. But this is actually kind of a tough question because it's, again, you're balancing what is the best thing to desire, right? Are you trying to get the maximum life? Are you trying to get the maximum performance? What are you trying to get out of the battery? We often recommend, when you're doing series and parallel strings like this, to first connect the batteries in parallel and then connect them in series, versus what's being listed here, where you have a string of 4 in series connected to another string of 4 in series. And the reason for that is now you have pairs of 2 batteries in parallel, and those 2 batteries are now always going to be at the same voltage. So battery 1 of string 1 and battery 1 of string 2 are at the same voltage. And this will help maintain the balance in the string longer when you allow the two strings, basically, I'll call it, to see each other's voltage. So say that battery one, string one, is a little bit weaker than battery one, string two. When you allow battery one, string two to pick up some of the load from string one, that means that the overall performance of the string is more stable. Whereas if you have string one that's really being pulled down by this weak battery, and string two is performing well, you're really going to start driving the health of those two strings apart. And then regarding the isolators, I think if I understand correct, you're talking about isolating one string of four from the other.
Yes.
That can help, but it needs to be actively monitored. That's kind of where the disbenefit will come down to. It goes back to the real world application. Are you able to have a person there or pay for the equipment to actively monitor the difference between the two strings to turn that isolator on and off?
Okay, I see. Yeah, that's definitely not applicable to us as well. Ours are out in the field that we're not able to access for sometimes months, depending on the training event.
Mm-hmm.
But yeah, the reason why I was asking about the isolators also is that kind of leads back also to the charging circuit as well.
Mm-hmm.
If I've got a charger that's charging these two banks, should I have an isolator between the charger and the banks?
It depends if you're asking from a safety or a performance standpoint. From a performance standpoint, in my personal opinion, you're not going to gain much, simply because when the batteries are if you can isolate them with a system of relays, more or less, to unconfigure them from series into parallel, which some systems will do, you're going to gain noticeable performance. But if you're just separating string one from string two, in my experience and opinion, you'd see better performance from just keeping those strings in parallel. But
Okay.
From a safety standpoint, you definitely want to be able to isolate the string from your system at a higher level.
Okay, yeah, and we have diode type isolators to protect the charger itself, but that was one of my thoughts, was for performance mostly. So,
Well, thank you.
Yeah, I think in your application you'll see the best. I'll call it increase in life or stability of life of the string if you pair the two 55 amp batteries into parallel, and then put those parallel strings into, or those parallel pairs into series, because you're allowing the two strings to help balance each other rather than keeping them independent.
right. Okay, thank you. I appreciate that.
Yep.
Well,
And then
thank you.
just to touch again on your charging voltage, of course I didn't bring a calculator in here, but for cycle charging, or I'm sorry, for standby charging, you're going to want 54 to 55 volts, and for cyclic charging, you're going to want closer to 58 to 59 volts. So it sounds to me like it's a float charge application. So I'd probably stay in that 54, 55 volt range for float charging.
Okay, perfect.
And
Thank
then
you.
and then for the initial charge current, if we talk about that 0.1 C, it'll be 1.1 amps, or C over 10, that's 1.1 amps.
Or 5.5 plus times 2, right? 11 point.
Well, yeah, so the batteries are in parallel, so it's a 110 amp hour string. And I should check my math, because that's 11 amps.
11 amps.
Not 1.1. I'm sorry. Yeah, so 11 amps for your initial charge current.
All right, great. We have one more question. This was Gang iPhone, where I guess it was a follow-on question. Are SLA statistics the same for automotive versus SLA? And if yes, any quantitative data? So let's unmute Gang, and let's understand that question a little bit better. And I think maybe, Bjorn, you might have explained some of this before, but
Yeah, so the batteries are very different in construction. So if you're using an automotive battery in a standby application, that application mismatch is going to cost you life. So the automotive battery is designed for high current applications, and we have very thin plates designed to deliver that super high current surge. If you apply that into a standby application where you are regularly float charging the battery, the corrosion is going to occur on those plates and you're going to lose performance. So for a standby battery, we use thicker plates. So there's less plates in the battery, but they're thicker. So while the batteries may weigh the same, that corrosion takes longer to affect the battery, and you'll get a better standby life out of that battery. But then if we talk about the reverse, if you try to put that standby battery into an engine starting application, you're not going to see very good CCA or very good cranking amps because there's not enough area on the plate to deliver that high current to the starter.
That's great. All right, great. I think Gang unmuted. Were there any other questions? We were able to answer that?
Yeah, sorry, I'm back. My question is, how about the data? Do you have any data, how long the battery would last? If we keep 50% for the lithium ion battery or 100% on the lead acid battery, do you have any data, the lifetime of the battery if we keep it float? Because we have an application, we want to keep battery floating all the time, for a long time, for 5-10 years for our power supplies.
Yeah, so for a float application, I actually would not recommend a lithium battery, simply because it's not using what the battery is designed to do. And I would recommend a lead acid. And then regarding your question about float life, we do have data we can share with you offline if you like to see how those batteries react. We have a product line that's designed to last 3 to 5 years in standby, and we have a product line that's designed to last 10 to 12 years in standby. And the difference between those two batteries is just the physical amount of lead in the battery that helps it last longer. And really what the life of the battery in standby comes down to is how you're treating the battery. So we can make a 3 to 5 year battery last 10 years by treating it extremely well. 20 degrees Celsius environment, 13.6 volt float charge, never discharging it. So never actually using the battery. And then it'll last 10 years, right? So it all kind of comes back to that balance of how you're going to use it. And as far as the data goes, we do what's called high temperature life testing. And we subject the battery to very high temperatures and cycle it. And we're able to actually connect that testing to real world performance and accelerate the degradation to show how the battery would perform under lower temperatures. And that's I don't have the IEC, the UL test number off the top of my head, but it's basically an accredited test by the Society of Engineers, and we run most of our models through that test.
I see. Last question for your lithium battery. They come with a balancing circuit from cell to cell, or nothing balanced?
Correct. Yeah. So our lithium batteries are fully protected with the battery management system. So we have what you're talking about now, the balancing system. So we're actively monitoring all the cells in the battery, keeping them at in perfect balance all the time. And then we also have protections over voltage, under voltage, over current charge, over current discharge, high temperature, low temperature, all of those items.
The balancings are active balancing or passive?
Some of our models are passive and some of them are active. So we'd have to work with you to understand which battery you're looking for, and then I could let you know more specifically, but it depends on which battery.
I see. The balancing current is like a 1% of the C, or 5% or 0.1%. To have that data?
Most of our balancing that's passive is around 1 watt per series cell. It'll depend on the battery, and then when we move to active balancing, it's again going to depend on the model. So we can get you that when we select which battery you'd be requiring.
Yeah. We like to know the number is 1%, usually 1% or 0.1% of the total current. We like to know the current.
Unfortunately, it depends on the battery model. I can't give you an answer just in general.
Okay, okay. Yeah, very good. Send me some info by email. I really appreciate. Thank you. Good seminar, good meeting, good
Thank
presentation.
you. Yes, it's our pleasure.
Yeah.
That's great. So while we're in Q&A, does anyone else have any other questions or comments on our talk today?
Mike, there's one more question in the chat from Anthony.
Sure. Let's unmute him. Are these battery management systems built into the battery case for the lithium? Yes, they are. Bjorn, do you want to just highlight that one?
Yeah, the lithium batteries will definitely be could be another 45-minute plus topic. So we'll keep it high level, but they are built into the cases for the batteries. Essentially, when you look at the battery, it looks like an SLA replacement. So our lithium 100 amp hour battery looks just like our lead acid 100 amp hour battery, but there's a lot more going on inside of the battery.
Okay, and do they have shut off for cold, inclement weather, like super cold, super hot?
They do. We turn off and we protect for low temperature charging and discharging, and we protect for high temperature charging and discharging. It occurs at different levels depending on the battery model.
Okay, and do they also contain warmers or no?
We do have heaters available on request, but those are make to order. We don't normally inventory them. What I usually tell people about battery heaters is in most applications, you really don't need it. And that's simply because unless the battery is sitting, not being used, the chemical reaction occurring of actively charging and discharging the battery will keep it above that minimum temperature threshold until you're getting really far north. So if you're in, northern Minnesota, North Dakota, Alaska, places like that, that's where you'll actually start to run into the problem. But I think the cold temperature charging, I don't want to call it a fear, but the cold temperature charging concern is a little overinflated in real world applications.
Okay. Thank you again.
Yeah, our pleasure.
Well, thank you, everybody. If there are no further questions, first, I'd like to thank everyone that stayed on and listened to the Q&A. I believe that this was a very informative talk. If you have any additional questions and you want to reach out to myself or Tom or Bjorn, you can reach us at 888-612-9514 or sales@trcelectronics.com. That's one word, sales@trcelectronics.com. We'd be happy to continue any type of discussion that you need or help solve any of your applications. So thank you all.
Absolutely. Thank you guys again. We appreciate your time.
Thanks, guys. Bye, everybody.